Hello, my name is Connor Healy and this video is about my project, Active Stabilisation of Motorcycle Roll Dynamics at Low Speeds. This project aims to solve problems that we have with traffic flow and parking shortages by making motorcycles more accessible to the general public so that they can be used on commutes. The method of actuation used in this project was steering control. Steering control uses negative trail length to cause the motorcycle to roll in the opposite direction that the handlebar is turned. In this project, a model-based design approach was used. This meant that instead of designing a motorcycle, building it, and then trying to control it, the motorcycle was designed with control in mind from the beginning. Such an approach always starts with a mechanical model. Here you can see the transfer function for the roll dynamics of the motorcycle. Looking at this transfer function, it is possible to optimize the design of the motorcycle to make it more controllable. Ways of doing this include having the center of gravity as far forward and low down as possible, having a negative trail length as discussed previously, and having the head tube angle as close to 90 degrees as possible. Low speed control of a motorcycle is difficult because the stabilisation effect from the wheel is absent. You can see when this wheel is not spinning, it's very easy for me to rotate it side to side. However, once I give it a spin, this movement becomes a lot more difficult. That's why it's easier to balance a motorcycle when it's moving. Another challenge with this control problem was that the zero of the roll transfer function is dependent on the velocity of the motorcycle. The result is that if the motorcycle roll controller is tuned for a certain speed and operated at another, there's a lot of oscillation present in the output. Therefore, an adaptive controller that changes the controller parameters as the speed of the bike changes is necessary. The motorcycle was designed to the specifications discussed earlier. Properties such as center of gravity and overall mass were exported to MATLAB where controllers were designed using root locus plots. The root locus is a design tool used by control engineers to help place poles and zeros to give desired controller performance. Of particular interest are natural frequency, damping, and settling time. The root locus also allows control engineers to check the system for stability. A cascade controller was used in this project, with an inner loop for the steering system and an outer loop for the roll system. You can see that the roll controller takes feedback from the motorcycle's velocity for the purposes of adaptive control. A simple classical control loop was used for speed. Transient plots generated in Simulink were used to test controller performance. The motorcycle was designed so the majority of its parts could be 3D printed. Dual extrusion with water-soluble support filaments was used. Most of the parts were printed using a rigid PLA material. However, a flexible TPU filament was used for the tires to give them more traction. An Arduino MKR1010 Wi-Fi microcontroller was used, along with its accompanying motor carrier and IMU shield. A rotary potentiometer was used for steering feedback. You can see here a test video for the motorcycle balancing while stationary. Both output plots show deviations from their set points. This is mainly due to a deadband and backlash in the steering gearbox, as well as the lack of a free integrator in the roll control system. Most of the time in this project was spent on design for control and manufacture. While these are areas I was very happy with, perfecting the control of the motorcycle is something that could use a bit more time. I would like to see it having better disturbance rejection at standstill, being able to maneuver more effectively while driving, and being able to balance with someone sitting on the bike. Thanks very much for watching.